Welcome everybody to Calculus BC. In today's episode, we're going to be learning about Chapter 8.2, which is Euler's method, made famous by Leonhard Euler for learning how to approximate values in non-separable differential equations, sometimes given by a slope field. Made famous by Leonhard Euler, but made only slightly more famous by one Katherine Johnson in Hidden Figures when she used Euler's method to calculate the trajectory of a space shuttle Apollo from the Earth to the Moon. So that was a pretty iconic kind of scene right there. And so we're going to use this non-separable differential equation. We're going to use Euler's method to predict a particular value on this function here. And so the way Euler's method works is I'm going to try and have us predict what is f of 2. All right, so we're going to try and find out what that is. Now, in order to figure this out, what we're going to do is we're going to actually employ a very similar system to how celestial navigators would navigate their ships. And so what we're going to do is we're going to navigate based off of this function's slope. And so we know that f prime at 0, right? So the slope, in other words, dy over dx at x equals 0, right? So at x equals 0, we have coordinates 0, 1, right? Which means our slope was 1. And so I'm going to go to the slope field real quick. I'm going to show you guys what that looks like real quick. Okay, so I've got the slope field all lined up here. So that slope right there is 1. Now, if I click on this dot here, notice how the slope changes as I'm moving, which is actually kind of a cool little deal here in Desmos. But what the slope does is it acts as my navigator. And so back in the old days, when ships would navigate using celestial navigation, is they would use two pieces of information. They would use a clock so they could figure out where the sun was at a particular time. They would align themselves with some kind of known thing in the sky, probably a North Star or some type of star that was easily recognizable. They would then angle that, find out the angle of elevation based on the horizon using a tool called a sextant. And what that would allow them to do with those pieces of information is it would allow them to calculate their position at a given point in time. Once they had their position, then as long as they knew where they were going, they could then set sail towards their objective for the day, because it was very much impossible. You weren't going to make it from Europe to what was then the new land, or wherever it is you were going back then. You just weren't going to make it there by sea in one day. So you had to set sail for as long as you could, anchor down, realign yourself, and re-navigate, which is exactly what Euler's method essentially does mathematically. What we're essentially going to do here is we are going to navigate based on one slope here, get to another position, and then figure out the new slope. Will this thing move? Okay, I was able to get it to move. So now we're going to set sail over this way, and then once we get to x equals 1, we have a new slope, right? We have a new navigation slope to get us to the next point. So when I get to x equals 3, my slope is going to be even steeper. Now, I'm actually going to do points that are even in between that. So let me show you guys what I mean by all of this. So we're going to try and guess f of 2. Well, what do we know about this differential equation so far? We know that dy over dx equals x plus y. It actually does say that up at the top. Let's say, for example, I wanted to navigate us from 0, 4. So from 0, 4. Let's say that's my starting point, right? That's going to be where I set sail from. My delta x is going to be the number of steps that I'm taking. The number of steps I'm going to take them by 0.5. So each step is going to be half an x value. And my window is going to be from 0 to x to 2. Of course, 2 being my objective. So what this is essentially saying is I'm going to start at 0, I'm going to sail for half a step, recalculate, re-navigate. Then sail for another half a step, recalculate, re-navigate, and just rinse and repeat that recalculation and re-navigation until I hit to 2. So the way this works is I'm actually going to go ahead and make a table. And I'm going to go and call this x for my x coordinate, y for my y coordinate. This is going to be dy over dx, which is my slope at that exact point in time. And then this thing is going to be odd. I'm going to call this new y. Now, new y is basically the position of where you are next. And so the way we find new y is going to be a little odd. I'll show you guys how to do that in just a second here. But let's fill out the information that we know. We know that my starting position of x is 0, and my starting position of y is 4. And so what I'm going to do here is I'm going to go ahead and calculate my slope at 0, 4. Well, that's easy. It's just going to be 4, right? The question is, how do I find this new y? What is this thing that's called new y? So what I'm going to do, remember what we're doing here is we are calculating a bunch of different linear slopes. So one slope to the next, one slope to the next. Well, remember back in integrated 1, we learned that slope can be represented by a slope triangle. So that slope triangle, whatever this slope is, has an m, and that's going to be caused by a delta y, a change in y, over a delta x. Now, let's hopefully clarify something here. Hopefully it makes sense that new y would be equal to whatever the old y was, right? Whatever the old y, plus the delta y, whatever change in the y is going to be. So if I added my change in y to my old y, I would get new y. Hopefully that makes sense. This is the thing that we don't know. But remember, we just talked about how in integrated 1, we have this slope triangle. So what I'm going to do is I'm going to go and solve for delta y using a relationship between these three pieces. Well, what I do know is that slope is created by a change in y over a change in x. And if I solve for delta y, I would just get delta x times m equals delta y. And that is what goes in for delta y. So what we say for new y is that we have m times delta x plus old y. And in books, what they tend to say as an actual formula is this. Y sub n is equal to dy over dx times delta x plus y sub n minus 1. So hopefully you can see the corresponding pieces, right? The new y, sometimes I might call it current y, and then of course the m is the slope, delta x seems pretty obvious, and then y sub n minus 1 is the old y. So hopefully the corresponding parts make sense. I don't know, I like this one. This one seems to make more sense. I mean, the notation obviously makes sense, but I do like I like the words. The words seem kind of neat. And so what we're going to do is we're going to follow this formula to go ahead and find out what new y is. Remember, new y is equal to m. So what's my slope here? My slope is 4 times delta x. Well, delta x was 0.5, right? 0.5 plus old y. Well, old y is the original y, so that's going to be 4. So that's going to give me 6. Now at this point, I can probably fill in all the x values because my delta x is 0.5. So I know there's going to be 0.5, 1.0, 1.5, and 2.0. And now this new y goes into this y's position, meaning I have coordinates at 0.5, 6. And again, that's just an approximation, right? And so again, dy dx, let's go and find out what dy dx is right there. I'm going to plug in 0.5 and y into here. That gets me 6.5. As you guys are guessing, you'll probably need a calculator for some of these more complicated calculations. But luckily, I have already kind of worked it out. That way I don't waste you guys' time trying to show you guys what what each calculation is. Remember, m times delta x plus old y, so plus 6 is equal to 9.25, and I'll go and just speed up the rest of it. I'm going to go, if you want, please feel free to pause and then try and get all the answers of new y before I do. So I'll go and just give you a second to pause real quick, but I'll do this one a little more slowly still, that way we get used to it. This 9.25 goes here. Dy over dx is going to be, again, 1 plus 9.25, so 10.25, and then again, I just plug it into my new y formula here. So new y is equal to m, so that's going to be 10.25 times delta x, so 0.5, plus old y, so 9.25. That's going to get me 14.375, and that is what goes in here, 14.375. Plug that into there. You end up getting 15.875, and then again, dy dx times delta x. So 15.875 times delta x, which is going to be 0.5 plus old y, 14.375. And then where you want to be careful is the result of this is your answer. So this ends up being 22.313. And so what happens is this thing here does not move forward. All right, we don't move forward because this answer right here would be f of 2.5, right? But we don't want that. We want f of 2.0. In other words, what this is saying is that f of 2 is approximately 22.313. And so what just happened here? Well, if we look at this as a graph, right? If we look at this as a graph, if we were to actually calculate all of these using slopes, I would put all these points in. So 0, 4, 0.5, 6, blah, 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 blah. And so I'll go and just put those in. So 0, 4, 0.5, 6, so 0.5, 6, 1, 9.25, 1.5, 1.5, 14.375, and then 2.0, 22.313. And so while I did compare it to celestial navigation, what happens is that because you're navigating using a linear slope, Euler's method is essentially a summation of a bunch of small linear approximations that eventually get you more or less to the place where you want to be. So of course, being more accurate, hopefully this will make sense, being more accurate just requires taking many, many, many more steps. So if I ended up having a delta x of 0.001, it would take a long, long time to get to 2.0, but my estimation would be a lot more accurate. So usually the step sizes are pretty manageable. They're like 0.5 each. They're not trying to get you to calculate a million things here. But yeah, that's Euler's method for you. I'll be right back with the next example. Give me a second. So in this example here, we're actually going to be using Euler's method backwards. So notice how we're given f of 2 equaling 8, and we're trying to estimate f of 0, right? And we're given this as our differential equation. So what I'm going to do is I'm actually going to go ahead and set up everything that I set up here. I just make a list. dy over dx equals 2x minus y. We know that y of 2 is equal to 8, or f of 2 is equal to 8. We want y of 0, and our delta x is actually going to be, since I'm going to be going from 2 to 0 with 4 equal steps, hopefully it makes sense that each of my steps is half each again. But this time I'm moving backwards by a half, so I feel like my delta x is going to be 0.5. And when that happens, what I'm going to do is I'm going to go and make my table backwards. And I'm going to start at 2, and I'm going to decrease each time. And this usually helps keep me honest on these. And so yeah, that's just kind of how I do it. So otherwise, it's just kind of a procedural thing. We just kind of use our Euler's method to get all the different new y's. And in case you don't remember from the last example, new y is equal to m times delta x plus old y. All right, so now we start off at 2, 8. Again, I'm going to plug that in. Now I'm going to move a little fast here. If you want, please feel free to pause the video, try and get an answer before me, and then just kind of fast forward to the end of this problem here to see if we end up matching up as far as the lesson goes. But this will end up being -4 if you plug in a 2 and an 8 into the derivative, which means the new y is going to be -4, so m times delta x, so 0.5, plus old y, so plus 8. The culmination of all this is going to give me a 10. If I plug a 1.5 and a 10 into here, I get -7. So again, -7 times -0.5, -0.5, plus old y, which is 10. I apologize, that's a negative up there. That's going to get me 13.5. So again, 1 and 13.5 into this differential equation right here is going to give me -11.5. And again, I did pre-calculate all of this. That way the video could move somewhat efficiently. But, I want to make sure that we're all aware of that. I am not by any stretch doing any of this in my head here. So from here, this is going to be 19.25. Again, 0.5 and 19.25 into here is going to be negative 18.25, negative 18.25. So I got negative 18.25 again times delta x plus old y, 19.25. And again, I get 28.375, and I am done. I will not go into this territory. I don't want to find f of negative 0.5. I know that f of 0 or y of 0 is approximately equal to 28.375. And again, using a series of linear approximations, I was able to estimate that this is what it would become. And so from here, what's happening graphically is I started off at 2, 8. So I'll put 2, 8, kind of low, but that's all right, 2, 8. And then I retreated back to 1.5, 10. And then I retreated again back to 1, 13.5. And then I retreated again. Whoops, that's the point right there. Then I retreated again to 0.5, 19.25. And I apologize. Maybe I need to move I didn't space myself out particularly well here. I'll just delete that, and I'll go and move my x-axis to about right there. That way the 0 is not all the way disproportionately away. Then this is going to be, I'll probably put them a little bit higher. That's 0, 28.375. And again, what was happening here, I was backtracking each time. And I know it looks a little bit linear, and I apologize. It's probably a fault in my estimation of distance of points. But in other words, the graph kind of looks like this. Again, Euler's method is that series of linear approximations, exactly like the way ships would navigate back using celestial navigation, not during celestial times. That sounds like a video game. But I think that's gonna do it for Euler's method. I think it's a pretty straightforward kind of thing. It's a lot of computation, probably requiring a calculator. So that'll wrap it up for this episode. As always, please leave comments or questions in the comments area. I will see you all in the next episode.